This is an application where we'll perform closed-loop control with National Instruments USB 6009. To do this, we'll need to acquire single points of analog input, perform a control algorithm, and we're going to choose one called PID, which stands for Proportional Integral Derivative, and then we'll issue a response with the analog output channel. So first, before we do this, I'd like to describe our setup, and this is a very simple setup. This is the USB 6009. Right here is our analog input channel coming in here, analog input channel 0, and we're going to be looping back to that from our analog output channel 0. So analog output channel loops over here into analog input channel 0. And that's our whole setup on the USB 6009. So let's go right into LabVIEW and set up our program. And LabVIEW is our graphical programming language that we use for data acquisition and control tasks. It makes setting up the simple ones straightforward and can also be expanded to more complex applications. So we'll go to our front panel and we'll start from scratch here. We'll click the right mouse button. We're going to put down a waveform chart, and we'll stretch this out a little bit so that we'll have some room to see it. And we're going to set the scaling from 0 up to 5 volts, and that'll be the range that we want to see. We'll also tell it not to auto scale because we don't want the scale changing while we're running. So that's fine, and that'll be our basic user interface. Now we'll go back to the block diagram and we'll jump right in. The first thing we want to do is be able to acquire input from the world. In our case, it's a loop back, but we know we can acquire it from any number of places. So we'll click the right mouse button. We'll go to Measurement and I/O, and we'll drop down our Data Acquisition Assistant, and this is going to allow us to configure our analog input. So we want to acquire signals. We'll do analog input, voltage, and then we'll choose an analog input channel 0, and we'll say Finish. Now we'll set up a few more parameters on this measurement. The input range for this device is plus and minus 10 volts. We'll tell it to be in referenced single-ended mode, and then we only want to acquire one sample at a time. So we'll do one sample on demand, and we'll finish that up. So right away, we'll go ahead and wire the output of the DAC Assistant function into the waveform chart, and now we know we'll be able to see that as it runs. The next thing we want to do is set up the analog output, and the way we do that is we click the right mouse button, drop down the Data Acquisition Assistant again, and this time instead of doing analog input, we'll tell it we want to generate signals, and we'll do analog output. So we'll choose voltage, we'll choose AO0, we'll finish on that. And now we don't have to set up too much except that we're going to just generate one sample on demand, and that means it's software driven. So we'll click OK on that, and we're set up and ready to go for analog output. Now we need to choose our control algorithm, and we'll select a simple PID algorithm, and we'll get this by clicking the right mouse button again, and we'll go down to Select the VI. Now PID is an algorithm that does control, and you can find out a lot of information on this at www.ni.com. We actually have a toolkit that makes this very comprehensive, and this is just a simple user-created PID algorithm that I'm using here. What we're going to do is, you can see from the help window that's come up that I have a bunch of parameters that I need to set for this. And the first thing that we're going to do is wire the input from our analog input into something called the process variable. So we'll just wire that right up to our Data Acquisition Assistant, and that means as I'm acquiring data from the outside world, we'll tell the PID routine that that's what's happening out there in the real world. Now we want to create controls so that we can adjust some of the values for all the PID. So this sets controls for the minimum value, the maximum value. The next thing that we'll create here is the set point, and this is going to be the value that we actually want it to be at versus what the process variable says the real world is at. And then there are 3 more that are the P, I, and D constant values, and you use those to tune your algorithm. So the next thing that we want to do is wire this up to our analog output. So down here at the bottom is our routine for analog output, or our function, and we'll wire the output of PID, and this now sends that voltage value out into the real world. But remember from our setup, if you look at our setup here, this is actually the output, and it's coming right back into the input. So there should be immediate response. Any delay we see on our graph would be from the tuning constants that we set up, or the tuning variables we set up on the front panel. So let's go to the front panel and take a look at this now. Oh, in fact, I do need to put this in a loop. So before we go to that front panel, let's put it in a while loop. And we'll put this around the whole thing, and I want to tell it to go until I click a button. So if I remember to do that, now we'll have everything that we need to run our program. We go back to the front panel here and we're ready to run. The things that I do want to set, my minimum is 0 and that's fine, but I want my maximum value to go up to 5. So that's going to limit what my PID can set as ranges or values. Next we want to go and set the P, I, and D values, and we'll set them at some numbers. We'll choose 0.1 for P, we'll set it 0.1 for I, and then 0.01 for D. And those are numbers I just derived by knowing a little bit about this setup. So the other thing that I want to do is go back to the diagram, and I want to wire up the set point value into my waveform chart. And the reason I want to do this is so that when I change that set point, I can actually see the values versus what the real world is. So we've added that in now, and my program's now complete and ready to go. So when we go ahead and run this, we'll actually see that white line being the analog output, and then the red line, which you can see there for a little bit, that's going to be my set point. So if we begin to change this, you'll now see the red value, which is the set point that I'm controlling. It's changing, and the system is then responding through the control algorithm to try to match that red value. So at this point, it's pretty responsive. If I was sending this out into the real world, I would expect my system to be in between this loop right here and be responding to the stimulus from the analog output into the analog input. So that's a pretty abbreviated version of doing control, but I think you get the idea. And that's how you do proportional integral derivative based control with the USB 6009.